Okay, guys, good afternoon. So this is our, Tuesday's lecture. And, let's start our lecture. So let's start. So as you can see in the last class, we looked at our electromagnetic wave equation, and then we saw that the solution of all, whether it is the electric field components or the magnetic field components, they follow this kind of differential equation, and whose solution is, in the form of z plus or minus ut, right? And then from there, we saw that this function, which is f z plus or minus ut, it is propagating in space, and also, as time passes by, and the velocity at which it is propagating is 1 over root of mu epsilon. And then here f can take any of this field components, and there are different solutions which are available, but we need to select the more logical solution that is required for our electromagnetic waves. Now we can try to think and relate it from our sources. So who is generating these electromagnetic waves? So therefore our sources are sinusoidal sources. So therefore the best solution to mathematically represent the electromagnetic wave is a sinusoidal solution. So you can go for this one, or this one. You can go for any of this. But again, from these, what we will do is we will just try to again closely follow our sources. So in our electrical engineering, our sinusoidal sources are mostly represented in a cosine form. So therefore, we will assume this as the solution to our electromagnetic wave, which is a logical solution for us because the main source of this electromagnetic wave is a sinusoidal source. Okay, then let's move forward. So therefore, what you will have, if you see here, now what we are doing is, now we are simplifying things, and you will see that these simplifications holds to some extent. First is, so our electric field E is made up of EX, AX, right? So I'm taking the Cartesian coordinates, thus EY, AY, thus EZ, AZ. But now what I'm doing is I'm simplifying things. I'm assuming that my electric field has only this component. So I'm assuming that these components are not there, just to simplify our solution. So therefore, my electric field has only X component. Moreover, I'm also saying that my EX, which is this EX component, it can be a function of X, Y, Z, and T, right? But what I'm doing is, for some reason, I'm saying that it is not depending on X and it is not depending on Y. Further simplification. And therefore, I'm saying that my EX is only a function of Z, T. So again, this further simplification, to some extent, when you go and when you look at some practical cases, simple cases, you will see that your X and Y, in fact, will be some fixed values, and it will not contribute much towards the solution of the wave equation. Okay, so it will be fixed. And we will look at this a little bit more when we go and look at the waveguides, the bounded medium. So you will see that X and Y, will be somehow bounded with the bounded medium, and therefore they will not contribute much towards the mathematical solution. And now this is our electric field, EX component. So I'm writing it as Z plus or minus UT. And then I'm assuming the sinusoidal solution. Therefore, my EX is E naught cosine omega t minus beta z. This is a standard notation. where E0 is called as the amplitude of my electromagnetic wave, omega is the angular frequency, and beta is a new term. So beta is called as a phase constant. Sometimes it is also called as a wave number, but in our book, since they are using phase constant, we will use phase constant. And the solution obeys this general solution, so therefore it is intact. And now if you further look into this equation, we will see that our electromagnetic wave is oscillating at a frequency of omega, which is equal to 2 pi f, and then it has a frequency of f, and then the time period. So omega is 2 pi f, the frequency is f, and also the time period. So time period is nothing but 1 over f. Okay. Now, as I told before in the last class, that the positive sign and the negative sign. So here, the positive sign and the negative sign. So here, the positive sign, the negative sign corresponds to moving in the positive z direction, right? And the negative sign, the positive sign here corresponds to moving in the negative z direction. This we discussed in the last class, right? So same thing here. So here I'm now assuming as f of z minus ut. So that's why I'm seeing it as minus. And therefore, this wave is traveling in the positive z direction. And the phase velocity u is given by 1 over root of mu epsilon. And it is also equal to omega over beta. And how we got this omega over beta, you will see it in a couple of lectures, okay? Now, suppose if you don't have negative, if you have positive. So for example, if you have, this E bar as AX E naught cos of omega t plus beta z. So in this case, your electromagnetic wave is traveling in the minus z direction. And just to let you know, see this minus z direction plus z direction that we are looking at it, this is just for the mathematical representation. Because when we are putting our electromagnetic wave mathematically on a paper, then we have to use a reference, right? From the reference, we have to say that it is moving in the right direction or it is moving in the left direction. That's why we use this minus and plus. So if you have a source on the left-hand side, then your electric field is moving on the right-hand side, moving away from the source, positive z direction. So that you want to put it on a paper, then you put it in this manner. Okay. Then I'm now going a little bit detailed into the phase velocity. And now what I'm doing here is I'm just trying to rewrite the phase velocity expression in terms of the speed of light. So I'm writing mu epsilon as mu 0 epsilon. I'm writing it as mu 0 mu r and epsilon 0 epsilon r, right? And for free space, so this is for free space. So, and for free space, we know mu is mu 0, epsilon is epsilon 0. And if you substitute this constants, you will get it as the speed of light. That means my electromagnetic wave travels at the speed of light in free space. Now, what about in any other medium? Then in any other medium, let's move mu 0 epsilon 0 outside. So we are separating, and this one, we know it is speed of light. So if I substitute this with c, it is root of mu r epsilon. So therefore, in any medium, your speed of light will be less than or equal to c. That is, this is in any medium. And this is in free space. So if your electromagnetic wave travels in any medium, then its speed will be less than the speed of light. And how much it will be less? It will be defined by the characteristics of the medium. Okay. Then we also look at other parameters of our electric field, which is E0 cosine omega t minus beta z. And from there, what we found is these things. So what are these things? First is the wavelength. So we have E bar is AX E0 cosine omega t minus beta z. So we just now looked at U, which is this one. Now the wavelength. So the wavelength is U over F. It's not C over F because we are not generalizing it for any medium. So it is U over F. And U, we just now got it. U is 1 over root of mu epsilon. It is also equal to omega over beta. So if I substitute here, omega over beta over F, so it will be 2 pi F over beta or 2 pi over beta. So your lambda is 2 pi over beta, where lambda is the wavelength. Now, time period, I have already told, t is 1 over f. And now I can write f as omega. Sorry, there is a mistake here. So f is 2 pi over omega is 2 pi f, right? So f is 2 pi over omega. So therefore, what you will get here, you will get as 2 pi over omega. Because f is in the denominator, so it is, I'm sorry, not 2 pi over omega, omega over 2 pi. Omega over 2 pi. Okay. So therefore, here it is in the denominator. So omega over 2 pi will be 2 pi over omega. Okay. So I think there is a mistake here, guys. So just neglect this part. Neglect this. So therefore, I can say that my time period is equal to 2 pi over omega. Of course, here you also have the expression lambda as u over f. And here also you have time is equal to 1 over f. Now there is an analogy, similarity between them. See, this we have been using several times in our electric circuits. And this is what we defined as an angular velocity is nothing but you look it in the angular domain where you will say that your, so your arrow, if it travels complete 360 degrees and when it returns back, that is your angular frequency. Okay, so that's why its unit is in, omega unit is in radians per second. Okay, so it will complete travel from the starting point and comes to the same point that is called as one oscillation, right? So this one oscillation, we put it under the umbrella of angular velocity with respect to 2 pi, right? So this is radians per second. So in a similar way, now we have it in space domain. So this was in time frequency, but this is in space. So in a similar way, we are defining this parameter called beta, which is a phase constant or a wave number, which has an analogy with lambda. So you can also think it in a angular, say, domain, where if your arrow travels from here till here, complete 360 degrees, one oscillation in space, then that one oscillation is in space is nothing but your lambda. And this is nothing but radians per meter. So if you make this complete one oscillation, that is your wavelength. Here, if you make one complete oscillation, that is your time. And in terms of angular velocity, it is 2 pi over omega. Here, it is radians per meter. So, wavelength, time, angular frequency, and the phase constant. Okay, so I hope it is clear to you. So because this is in the angular domain, that's why with respect to 2 pi, so if you make one complete rotation, that will be equal to the 2 pi 360 degrees, and that is nothing but one time period. Here also, you make one complete rotation, which is nothing but 2 pi radians or 360 degrees, and that will be equal to the one wavelength. Okay, so this is the space-time analogy. Now, let's take an example. So in the example, it is saying that we have an electric field, and the electric field vector is given by E is AX 20 cos 10 to the power of 9t plus beta z. And then you are asked to find the various parameters of the electric field. So if you see here, so it is asked to find first, so this is given to us, and we are asked to find field amplitude. So let's compare this with our standard. So which is E bar is AX E naught cosine omega t plus beta. It's okay, no problem. So therefore, my field amplitude compared here is nothing but 20 volts per meter. Direction of propagation, it's positive. So positive means it is going in the minus z direction. Because it is positive and here it is z. So that's why minus z direction. So minus z direction. Phase velocity, u, because it is in free space. If you can see this, it is in free space. So we know it very well. The phase velocity will be same as the velocity of light. So 3 times 10 to the power of 8 meters per second. The phase constant. So if the phase constant u is omega over beta, or the beta is omega over u, or in our case in the free space it is omega over c, and that will be 3.33 radians per meter. Okay, and the wavelength. So how can you find wavelength? There are several expressions. You can use any expression to find the wavelength. So in this case, you can use lambda is u over f. The frequency, you have the frequency here, u over f. And then from there you can find, which is nothing but c over f, or lambda is 2 pi over beta, because you also got beta. So you can use any of them. This is another example where the electric field vector is given to you, which is this one. And then it exists in a medium of non-magnetic, and it is epsilon r is 9. And the wavelength is given to us. So lambda is 2 meters. And then we need to find the phase velocity. So how do you find the phase velocity? C is, u is c over root of mu r epsilon r. So because it's not in the free space now, see, it's not in the free space. So that's why we have to use the generalized expression, and which is c over root of mu r epsilon r. If we substitute these two, and this is the velocity. And as we can see, the velocity in this medium is less than the velocity of light. Then phase constant beta is 2 pi. So lambda is 2 pi over beta, or I can say beta is 2 pi over lambda, and lambda is given to us 2. So it is 2 pi over 2, that is pi radians per meter. Then the last thing is the angular velocity omega. If you look at it, it's not given here, omega. But I can use this expression because I know the phase velocity, and I know beta. So omega is what? Just u multiplied by beta, right? So u is 10 to the power of 8 times beta is pi. So it is pi 10 to the power of 8 radians per second. And the direction of propagation, look at it. It is, look at here, it is negative, so positive. And which direction? Z. So it is positive Z direction. Okay. So this is only for the electric field. Now we need to find the magnetic field, because as I told you, now the electric field and the magnetic field, they are coupled. Coupled means they are becoming the source of each other. So they sustain together and therefore they will exist together. So till now we were looking at the electric field, but how can we find the associated magnetic field of that? So the associated magnetic field of that, again, you can do the same thing. You can go to our, this expression, see, go, take this, our, the 1D scalar wave equation, and then you just solve it for the magnetic field. You can solve it for this, you can do it. And now here we are finding the associated magnetic field. Rather than going into the wave equation, we are just using the Maxwell's equation, which is this one. See, del cross E is minus 2d bar over dou t, which is del cross E is minus mu dou h bar over dou t. And this equation is telling us, we know it very well, this is becoming source of this. And the other next equation, which is del cross h bar, is how much? Is what? J bar plus dou d bar over dou t. And here again we are seeing that the magnetic field is becoming the source of the electric field. So that's why they are coupled and they sustain together. Now, if this is my electric field, then my corresponding magnetic field will be very easy to find. Just put it in the Maxwell's equation. So this is known to me. I need to find this. So del cross E, sorry guys, this has to be modulus, is minus mu dou h bar over dou t. So here my electric field has only x component. So therefore Ex 0, 0. And if I expand this, I'm only seeing one term, which is the y direction term. So this is telling me that this one, which is your right hand side, h bar, which I can write it as hx plus hy plus hz. So since my left hand side has only ay term, so my right hand side will also have only ay term. So therefore this and this automatically go to 0. And then if I equate it, I will get ay bar dou Ex over dou z is equal to minus mu dou hy over dou t ay bar. Right? And then when I equate these two, I will get this. And let us now do a further simplification. So when you do a further simplification, what you will see the following. So you will see that when you do the further simplification, you are finding this differentiation with respect to z, keeping the right hand side as it is. And then after doing a few simplifications, you will see that my hy will be equal to beta over mu omega E naught cos of omega t minus beta. But we know that E bar is Ex, which is Ax E naught cos of omega t minus beta z. So therefore, I can say that this is nothing but my Ex. So that's why I'm replacing it with Ex. And here I'm substituting omega over beta with u. And then I'm opening u as 1 over root of mu epsilon, and I'm seeing that my hy is ex over root of mu over epsilon. And this mu over epsilon is called as eta. And this is called as the intrinsic impedance of the medium, which is, you can think it like, a sort of impedance that your electromagnetic wave will experience as it travels in the medium. Okay, and this relates the electric and the magnetic field amplitude. As you can see here, this is amperes, volts per meter, this is amperes per meter, and therefore it is ohms. And this is my associated magnetic field for my electric field, which is cos of omega t minus beta c. So this is my electric field, and this is the associated magnetic field. So they are together. Okay, they are together. Now, next, what we did is we tried to find the intrinsic impedance of free space. That's why it is called as eta 0, is nothing but root of mu 0 over epsilon 0. And we see that it is 120 pi or 377 ohms. So this is the the sort of impedance that your electromagnetic wave will experience when it travels in free space. And if you want to generalize it, so the root of mu 0 mu r over epsilon 0 epsilon r, which is nothing but eta 0 root of mu r over epsilon. Okay, and now looking about the directions, and other things, and we will take this example and this direction we will discuss in our next class. But now I just wanted to focus a little bit. I will just try. I want to just give you an idea about what does this traveling wave looks like, where it is this one. This traveling wave looks like cos of omega t minus beta c. How does it looks like? Because in our previous lecture, I gave an example of a function, so we did not decide whether my function is a sine wave and cosine wave. I just said that it can be any function, and we are seeing that this function is traveling with, as the time is increasing, this function is traveling along a space direction, which is z here. So now, since we have decided that our function f is a sinusoidal, how does that looks like? So let's just look at it. So this is what I wanted to show here, a traveling sine wave. And these things are already there in your, so this is already there here. These things are already there here, where it is in the course extra material. So these things are already here. You can use it, you can check it. So here I'm just trying to show you how a sine wave looks like. So if you look at here, let's try to see here. Now here what I'm doing is I'm now freezing my space. Okay, so this is an example where my direction of propagation is x. So my x is the direction of propagation. The direction of propagation. Okay. And now what I'm doing is let's freeze x and then release t. Okay, so let's just release t, freeze x, and see what will happen. Now, if you see here, this is what's going to happen. So when I start, this, now I want you to look at only the purple part because I'm freezing x. So my x is froze here. So x is constant. So when x is constant, as you can see, my purple point is oscillating, right? my purple point is oscillating. Again, I'm showing you. See, my purple point is oscillating as the time has. Now I'm releasing the time. So it is oscillating. And what kind of oscillation this purple point is doing? The oscillation is nothing but your sinusoidal oscillation in time. And you can think this in the omega. You can think this as your, so the angular frequency, the rotation of this arrow. So here, this is how it is oscillating when I freeze time and release, freeze X and release time, because we are freezing X, making X a constant, and then just monitoring this point. Then we say that it is oscillating, right? Now let's do the other way around. So now this is the case where what I am doing is I am now freezing time. So what I am doing is in my cosine of omega t minus beta z. Guys, please don't confuse, because here everything is shown is with respect to the direction of propagation as x, but it doesn't matter. So in our case, it is z. So if you want, okay, let me put it as x, omega x. So here now I am freezing time. Time is constant. And then my x is released. So if this is becoming a constant. Or think that, both of these is giving you, say, a value of, say, 90 degrees. So cos of 90 minus theta. So cos of 90 minus theta is sine theta. That means sine of beta x, right? And therefore, now, if you see here, when I now release x, I will allow my x to move. Then what I'm seeing, see the purple point? Now the purple point is moving along the x direction. This is your x direction. So now I'm releasing x. So x is not changing. But my time is a constant. I have made my time a constant. Then it is traveling in this like this. And this is the wavelength. And if you want to put it in the angular form, then it will rotate one complete rotation when it goes from here to here. And this is nothing but your phase constant, beta. Okay, so this is how we did when we, froze either time or the space, right? But now if we release both of them, then what you will see. Okay, so these are other animations also, which is giving you an idea of what is going on. If you want, you can have a look at it. But if we release both of them, then you will see a sine wave of something like this. Okay, so red. So this is a sine wave where your electric field E bar is E AY E naught cos of omega t minus beta x. So it is in the x direction. And my magnetic field H is equal to AZ H naught cos of omega t minus beta c. Because AZ is AX. Okay. So this is my electric field and the associated magnetic field. Now let's see. So this is also sinusoid. This is also sinusoid. They are coupled. They are coupled. They are going together, and they are going in the, sorry, they are going in the positive x direction. So they are going in the positive x direction, which is in positive this direction. Now, when I release both time and x, see what happens. Now, when I release both time and x, see what happens. So now, if you see here, you know, your eyes, you know, you are seeing that as if your sinusoidal wave is moving forward. It is moving forward along the direction of propagation. It is moving forward along the direction of propagation. And if you want, you know, if you just focus one arrow and look at that arrow, that means you are freezing x. And when you freeze x, then, you know, this oscillation that this arrow is doing, this is with respect to time. This is with respect to time. Okay, so this is called as our traveling field. So this is your electric field and this is the magnetic field. Okay, now there is one more thing, you know, guys, which which I wanted to tell you. This is called as the plane wave. So what does that plane wave means? See, what we are doing here is we are looking at it as a sinusoid, right? But in reality, you know, in reality, it's a 3D structure, right? So in a 3D structure, so here what I want you to focus is, I want you to focus the following, that if I now play this again, okay, so now what I'm trying to show you is this one. So see here. So now, you know, if you look at this peak, your peak is moving in time, right? So you are just selecting one point and following that point, right? But this point belongs to a plane. This point belongs to a plane. So if you see this point in a plane, it's something as if that your planes are moving forward, right? See, the planes are all moving forward. This is an example where we are just looking at a particular point and see how this point is moving, right? Now put it in a 3D. So this point will be somewhere here, right? And then it belongs to a plane, and this plane will be moving. Okay, guys, so this is what I'm telling you, that the sine wave that we have just now, saw, okay? Now, if you now try to visualize that sine wave, then, you know, this is what I wanted to show you. So if you visualize this sine wave, yeah, if you visualize this sine wave, now if you see here, what is happening? So this point, this is what I'm saying. See, this point, it belongs to a plane, this green plane, right? So now don't look at as one point, look as a plane. So this point belongs to this green plane. Then again, you have another point here, you know, of your sine wave, which is at the lowest peak. And that is shown by the red plane. Then again, you have a positive peak, which is shown by the green plane, and the negative, which is shown by the red plane. So now think it from the 3D. So rather than point, think it in 2D form in this direction, 2D, and overall look it in 3D form. So instead of point moving in a sinusoidal, you know, in a sinusoidal motion, think that the planes are now moving. Okay, and these planes, they will have a constant phase because their argument, anywhere where you go, the argument is cos omega t minus beta z. So the argument omega t minus beta z is the same. It is same everywhere. It is same everywhere. Okay, so it's a constant phase. Wherever you go, the phase is a constant. That is omega t minus beta z. So omega t minus beta z is a constant. And this green plane is that constant phase plane. This red plane is also a constant phase plane. The only thing is, in this green plane, which is a constant phase plane, your electric field is, think that it is reaching the maximum positive value, and this is maximum negative value. And between these also, you will have several planes. Now think from the plane's point of view. So therefore, each of this point on a sinusoid will correspond to a plane. And each of this will correspond to a plane. Each point belongs to a plane. I'm just showing the maximum value plane, which is green, and the minimum value plane, which is red. But they are made up of several planes, right? Now, what we want is if we somehow, so let me first erase this. So now let me release the time as well as the space. Let me make Z variable and let me make time also variable. So if I make Z and time both as, if I release it, then see what happens. See, these are all the planes. But as I told you, the red belongs, the maximum color, you can think that maybe how should I put it? So maybe you can think this, the darkest, as the negative value and the brightest as the positive. And now if I release in X, if I release the time and if I release the Z, then see, this is how the planes will be moving. Got it? This is how the planes will be moving. So in this, again, I am repeating. So here if we assume, we can assume it. We can assume maybe this is my negative cycle and this is my positive cycle. So let me assume this as my peak maximum. Okay, peak maximum, this one. So this is the minima and this is the zero and this is the zero. And for the blue one, let me assume this as the peak minimum. So it is something like this. So this point and then this point, it's negative. So this point, this point, this point. So this each point is a plane. Can you see this? So this is our sinusoid, which I showed you. Now, instead of a point and showing it in a sine wave manner, we are looking it from the point of view of a plane. And then if we release this plane, if we release the time as well as space, then see, the plane is now moving. See, they are moving in this direction. And since if I move anywhere in the plane, my omega t minus beta z is fixed, is a constant. And that's why it is called as a plane wave. So I think that was the explanation of the plane wave, where you can look at it. If you want, you can also see the plane wave in this direction. See where you can assume that the green is the negative part and the red is the positive part, and see how it moves. And another very good example of looking at a plane wave is, once you throw stone in a water palm or in a sea, then around the stones, you will see the waves forming, right? And these waves will be traveling. But around where the stone got inside the water, it is circular. But as it goes farther, it becomes straight and it becomes like this. This is a very good analogy of plane waves. Okay, these are called plane waves. These cannot be the plane wave because see here, the Z is changing. In our case, in a plane wave, wherever you move in the Z, the phase must be the same. Okay, so this is the plane waves. Okay, so these are called circular waves. In our Cartesian coordinates, this cannot be treated as a plane wave. We have to look it in the spherical coordinates to understand that. But in the Cartesian coordinates, if you look at them, then it's difficult to say that they are plane waves. So these are the plane waves. Okay. So I think with this, I will stop my discussion of this lecture, and we will meet in the next class. Thank you.